Thank you. Uh, Today we have Dmitry Rumynin from Warwick Mathematics Institute, and will tell us about C2 graded groups, real representations in Dyson's tenfold way. Thank you.
Oh, thank you for inviting me. This top picture is picture of Warwick University. This is mathematics department. This one you recognize. I really love Istanbul, but I've been there 3 or 4 times. And every time I stayed at Taksim Square. So that's Taksim Square. And that's a picture of a city by David Schnell. And in the title, the word real is capitalized for a reason. It's a tier real. It's different from real, from small letter, which refers to real numbers. So let me explain the structure of my talk. There will be 7 parts. I'll explain what the problem is. I'll give a little bit historical origins, example, and then I'll talk about A, L, H, and 2 representations of graded groups. It's based on these 3 papers. It's slightly, anyway, so the earliest paper is with Matthew Yarn, where we've done it for 2 representations of 2 groups. And then later, I did it with undergraduate student for the representations, for normal representation theory of C2 graded groups. Let me push forward. What is a group? A group is a category with 1 object. Yes, so it's 1 object, and every morphism is invertible. In that language, what is a representation of a group? A representation of a group is a functor from this category with 1 object to a category which you are interested in today. So in particular, key target categories for representations of group are finite dimensional complex vector spaces or 2 vector spaces. Cool. Now, what is a C2 graded group? It's just a group with a surjective homomorphism to a cyclic group of order 2 elements plus and minus 1. So it has the kernel, a coset of even elements, and it has a second coset of odd elements. But the key difference is you want to think of a 2 graded group as a category with 2 objects. So it's a category with 2 objects like this. So it has 2 objects. Even elements are homomorphism from objects to itself. Odd elements are homomorphisms between objects. This category also has an involution, pi, which swaps 2 points. And this involution can be made covariant or contravariant. Yes, so to make it covariant, that's how it should act on morphisms. To make it contravariant, you take the inverse. That's what a C2 graded group kind of thinking categorically. Now, to consider its representation, we need to look as functors of categories with involution to another category with involution. And if we consider finite dimensional vector spaces over complex numbers, then this category has 4 involutions around. Yes, so what you can do, you can take, well, so it's just identity, then we just get usual representation of this theory, classical, as ancient Greeks knew it. Then for a vector space, you can take its complex conjugate vector space. We call it antilinear representation, so A theory. We can take the dual space. This will be linear representation, L theory. And we can take dual conjugates, that's H theory. And then I'll talk about two representations, but essentially the task James Taylor and I set to do, we wanted to kind of figure out what's happening with these three categories. And as an easy example, oh no, that's a historic origins. So essentially it came from three different sources, this theory. So the oldest one is this in physics, and in physics they are known as co-representations. It was started by Wigner, but the fundamental paper is by Freeman Dyson, and that's the paper from 1962. Amazingly, Dyson managed to work it out completely, not knowing any algebra, because algebra which corresponds to this appeared slightly later, and this is a paper by Wall about graded Brauer groups, 1964. And that's Wall, that's Dyson. This is Atiyah and Segal. And that's the 1969 paper where this Principia is a topology, an equivariant K theory, and in particular KR theory. So these are three origins. Let me explain a little bit more about physics origin of that, and the other two I'll disregard for the talk today. So in physics, essentially, these are called co-representations, and it's what we call A theory, and they fall in what's known as Dyson's tenfold way and Wigner's threefold way. Here is one interesting paper on topological insulators. And okay, so none of my papers has 2,500 citations. This one does. Essentially, in this paper, they classified theories. They classified out of which ways out of the 10 Dyson possibilities, which theories can support topological insulators. I'm not going to say more. It's not something I understand. But here, let's consider a system, a physical system, that has a time reversal symmetry. So this is a good example. Yeah? So something is falling down, yes, then you can reverse time, and then it's going up, and it's described by the same physical laws. And when you quantize such system, then time reversing symmetries may act by antilinear operations after quantizations. And that's what these co-representations are. So essentially your symmetry group has two cosets, time-preserving cosets and time-reversing coset. And in quantization, G0 acts by linear operators, G1 acts by antilinear operators. And this is exactly A theory in our terminology. And this is where Dyson worked out its tenfold way. Any questions at this point? No? Good? Okay, let's consider the baby example. The simplest group there is around. Yes, take a group of two elements, maps identically to itself. So there is only one element to represent, X. So in all four series, it acts on a X have to be acting on a vector space, n-dimensional vector space, and it acts by square matrix. But what it does with this square matrix is slightly different. And here it's how it's different. So in the usual theory, that's the formula. And the fact that x squared is equal to 1, the matrix has to be, its square has to be equal to 1. So in A theory, x has to act by antilinear map, And a matrix can represent antilinear map, but the fact that x square is equal to 1 manifests in this algebraic condition on your square matrix. In L theory, somehow x essentially acts by, it sends V to its dual, right? So, and this will be the formula. And the algebraic conditions that x square equal to 1 manifests in this condition. So A is essentially non-degenerate symmetric bilinear form. And in H theory, that's the condition. And algebraic conditions become this, and this is non-degenerate Hermitian form. And you can see immediately some similarities between usual theory and H, and antilinear theory and linear theory. Because, so here you get a real structure on a vector space, and it's essentially unique up to isomorphism. Here you get a non-degenerate quadratic form over complex numbers. It's also unique up to isomorphism. And here, you're going to get a gradient. And there are n+1 possible gradients on a vector space. And here you get Hermitian form, symmetric Hermitian form, and there are n+1 possible signatures. So that's the key to understanding what's going to happen later. Any questions on this slide? Good. Okay, so let me concentrate on the blue picture, on the A theory now. So the next part of the talk is A theory. So A theory is, well, it's something we used to. All we have to do, we have to take a twisted, the group G, remember it's graded, so it has two cosets, G0 and G1. And then we can do semi-direct, what is it called? Few group algebra with complex numbers. Yeah, so this is a multiplication in this group algebra. So if G is even, nothing happens. And if G is odd, then you do complex conjugation. Then inside this semi-direct product, there are four subalgebras. Yeah, so CG0, RG, RG0. And these are four algebras one has to look at. Essentially what happens is these three algebras, this, that, and that, are real algebras. They're not complex. So this is a complex algebra. And these two algebras are graded because there are pieces which belong to G0 and there are pieces that belong to G1. And this is degree 0 piece. Yes. So essentially by staring at this square gives us Dyson tenfold way. How? Because essentially A representations of G are just representations of this C star G algebra. And what we can do, we can have to look at a block in these three algebras. Essentially, a sneaky way to define what the block does is consider the idempotent E, which is central among all the three. It lies in all of them, and it's central in all of them, and it's minimal among such. And then we have this kind of pieces, call them A, B, C, and D. So these three are real algebras. And this is complex algebra. And so essentially for each representation, there will be one such block. And the way Dyson was looking at the problem, he was essentially looking at algebras A and D, but the best really algebra to look at is B. B is a key algebra to understand because it's a graded matrix algebra over graded division algebra. Who is a graded division algebra? It's a C2 graded algebra over reals where every homogeneous element is invertible. And graded matrix is just matrix algebra, but there are various choices of grading. Yes? And what Terry Wold has done, he classified this graded division algebras, and the answer is what you would expect. Let me show the answer on the next slide. There are essentially only 10 real graded division algebras. There are usual division algebras, reals, complex numbers, and quaternions, all sitting in degree 0. Then there are 3 of those, so where R, C, and H are sitting diagonally. There are 3 opportunities like this. Then you can have a graded division algebra, R sitting inside C and C sitting inside H. And then there are 2 remaining possibilities. Your complex numbers could be inside M to R and H inside M to C. And again, you can put a gradient on M to C so that H is a grade 0 piece. And the real that there are only 10 real graded division algebras gives Dyson 10 way. How? Let's look at this. Essentially, it's all possible. That's how we introduce Dyson tenfold way. Dyson has done smart calculations with matrices, and Dyson notation is slightly differently. So let me show the previous slide. Essentially, FA, FB, and FD will be the corresponding division algebra behind the graded division algebra. And here it's always complex numbers. What Dyson was doing, he was looking only at these 2. So for him, type 1, he called it RR. This is called RC. There are 2 possibilities where these 2 match. This is called CC1 and CC2. But for us, I think this is more, FB is a bit more interesting. So for example, these three of the Dyson types RC, CC2, and HC, are just algebras without odd elements. So these are usual division algebras where gradient is trivial. And here, in these 4 columns, we list the number of simple modules in a block. Again, if I go back, you see there is algebra A, B, C, and D. They don't have to be simple. They may have more than one simple module because E is a central idempotent in all 4 algebras. And this is the number of simple modules in each block, right? So let's go and see all the other ones, what are doing. So then there are 3 of them where a field sits inside the field square as a diagonal subfield, and you can see them by having 2 modules here. So this is where you can recognize them. So, and these are corresponding Dyson types. These are RR, CC1, and H. Then there are 2 more. So this is real is inside complex and complex inside H. Here, I think it's easier to see by this pair. So this is real inside complex and complex inside H. And these are the examples of this block. Yes, C, C2, C2, and C. And this is an example of this kind of antilinear block. In the paper, we also give the smallest possible group. where you can observe such a block. We have a list of smallest possible groups to observe the structure of each block. And then the last one, the last two, is where you have complex numbers inside 2 by 2 matrices and H inside 2 by 2 matrices. And again, you can see it somehow. For me, this is where I would look for them, because here C goes to R, H goes to C. And these are Dyson types CR and HR. And that's a typical structure of this block. So this is our main result in the first paper, and this is a complete classification of A representations. Well, I mean, for each particular group, you have to work a little bit harder. We've done some work for alternating group sitting inside symmetric groups. I had an MSc student who has done some calculations for various binary dihedral groups and binary icosahedral. But in terms of what needs to be calculated, this table explains everything. Any questions? Good. Now let's go and understand the other theory. So this is antilinear theory, where odd elements act by antilinear representations. What happens if they act by bilinear forms? So this is what we call L representations. Roughly, what happens here? Every G and H on a vector space act by representations, and odd elements on this vector space act by non-degenerate bilinear forms. Right? That's what they do. And so here I write all the compatibilities between even elements. The compatibility is like this, but if there are two odd elements, this is a compatibility. So, and cool. So clearly you can see that the category is not linear, but let's define the category first. There are two versions of this category. We call it usual and strong. So the strong works better in terms of functorial description. So these are linear transformations of functor, but then there is a weaker version, which is usual. And in the usual one, a homomorphism from one vector space to another, F, would have to be a homomorphism of G0 modules, and it would have to preserve all bilinear forms like that. In the strong version, well, it will have to preserve these bilinear forms on V and W, or on V and on the dual, and this makes it invertible. Essentially, this usual one we call LRAP, and the strong one are essentially only isomorphisms in LRAP. Note that in the usual one, because all these bilinear forms are preserved, all the maps have to be injective, right? And here they all have to be bijective. Now, how do we describe this category? And we describe it with while unitary trick. We essentially can choose. So you take, let's do it. Let's see if I can see better. So we are going back to A representation. Yes. So this is an antilinear representation of this graded group. And for each antilinear representation, we can choose G0 equivalent Hermitian form on each reducible representation. And then we have this new category of representations of G with this form, and the form is preserved, call it A star rep. And the key observations that this A star rep, so these are antilinear representations with a form, and the maps which the form is preserved would have two forgetful functors. This kind of funny category. It's not as funny in topology. It's actually very important category. So when one works with equivariant spectra, this is these are the sort of things you do. So then it has two forgetful functors. One is to L representations, yes, which we can just forget about this form, right? And let's talk it slowly. So this was psi is where you just forget the form, right? And you don't only get map between A representations. You are going to get injective maps. So this category of monomorphisms inside A representations. And then you have a second functor to L representations. And for that, you have to get all the forms, yes? You need bilinear forms for odd elements, and you define them by this formula. And then after that, you forget this form, and you forget the action. So here, this functor, which is not completely forgetful, so it needs new definition, and then you define all structure. So there are these two functors. Is it clear? Questions? And here is the main theorem. That these functors are equivalences essentially of infinity categories. So it's kind of baby version of infinity categories. In other words, all these functors, all these categories, and these functors are enriched in topological spaces. And these two functors, phi and psi, are equivalences of categories enriched in its homotopy types. So essentially, on objects, they're essentially bijective, the functors, and on morphisms, it's always homotopy equivalences. So the category L rep and A rep are equivalent as what's called topological category, homotopy equivalent as topological category, or equivalent as infinity categories. And if you want to have isomorphisms inside these two categories, they also be these two, the strong versions of the categories. The strong version of the L category is the same as the category of isomorphisms in A representations, up to weak homotopy equivalence. Questions? No? Good. Now, and a similar picture is true for normal representations and Hermitian representations. So this is H. It will be very quick. It's very similar story. So again, here we just we put unitary trick. Yes, using this a category of representations of G with a fixed Hermitian positive definite forms. Then it has forgetful functors to monomorphisms in representations and to H representations, defined in a similar way. inside these two categories, there is a strong version of H representation and the category of isomorphisms inside representations. And here we have equivalences of infinity categories. And essentially, again, for each particular group, some work needs to be done, but the general framework how all four representation series behave is clear from our two papers. Questions? I'm somewhere in the middle and have to go to two representations now. Good. So it's interesting, as I say, so for me, because we understood two representations before, but only for one particular automorphism, involution. So let's look at this. So let's treat a C2 graded group as a two category with two objects and trivial two morphisms, as before, the same picture. And all two morphisms are trivial. As before, there are four different involutions. Okay, there are no two morphisms here, but still you can think of it as a contravariant of two morphisms. So this category has four different involutions because it could be covariant, contravariant on one morphisms and covariant and contravariant on two morphisms. And then a representation, a two representation of a C2 graded group is a two functor into another two category with involution. And the key two category is two vector spaces in this case. And as a note, Jan and I actually worked with, the paper works for any two group with a finite fundamental group. As soon as the first fundamental group is finite, we worked out this category in detail. And so let me explain what we have, let me explain what we have done. So for that, I want to explain quickly two vector spaces. Two vector spaces have different models, and I pick my favorite one because for this explanation, it's the clearest. Because here you can see all the possible involutions. So what are two vector spaces? Its objects are natural numbers 0, 1, 2, blah, blah, blah. One morphisms, then, are matrices of finite dimensional vector spaces. Yeah, so morphism from N to K. Yeah, so I think of standard vectors as columns. So this is K by N matrix, but each entry of this matrix is a vector space. And two morphisms are matrices of linear maps. So if we have a matrix of vector space of two matrices of vector spaces of the same size, then we can have a matrix of linear maps. These are two morphisms. And then 1 and 2 compositions are like this. The two compositions are on the nose. You just compose the maps. And for one composition, you have K by N matrix of vector spaces, an MK matrix of vector spaces, and you produce M by N matrix of vector spaces. And it looks like the usual formula, but with tensor product instead of a product, and direct sum instead of a sum. So this is a category of two vector spaces. Questions? Good. This category has 8 involutions.
I guess Professor Ikeda has a question.
Yes.
He wrote in the messages, in the chat.
Oh, in the chat. Okay, I'll try to read it in the chat. If it's two vectors, no, it's not Bayes-Kranz. I think Bayes-Kranz is another one. It's equivalent to Kapranov-Voevodsky, but slightly different model. It's not Bayes-Kranz. Yes, so Kapranov-Voevodsky have a completely skeletal model. And here the model is kind of skeletal at level 0. Yes, so I take in each dimension one object, but somehow for one morphism, I use non-skeletal version. Yes, I think it's just cleaner. It's easier to understand this. Well, so it's Kapranov-Voevodsky. Did I answer? Good. Now, what are the 8 involutions on 2 vector spaces? Oops, no. Essentially, here they are. If you think of one morphism, it's a matrix of vector spaces. You can do 3 basic operations. You can transpose the matrix of vector spaces. You can take the complex conjugates, or you can take their duals. And then you can do any combination of all these 3, right? So you can use this or not use, yeah, so 2 times 2 times 2, there are 8 possible involutions. So there are 8 different series. And with, for example, this will be standard ungraded series. Nothing happens, yes. So this is the same. I think it might have been done by, these are just representations of 2 representations of 2 groups, no graded. The one which we worked out with Matt Young is this involution, which uses transposition and duality. And we also had a plan to work out this involution, but never wrote it. So it's still unknown. And I think it's the most important of the remaining 6 involutions because it's related to Hermitian-Morita theory. And I can't say much about the remaining 5 involutions, but they are all probably an interesting problem to work out what's happening. Questions? Okay, now I'm going to explain the answer for the green involution. And the answer is actually very nice, I think. So I will go. Okay, so take any associative algebra A. Any associative algebra A. Then, to this associative algebra A, you can associate a natural C2 graded to group of its automorphisms. So what I write here is a crossed module, and crossed module is one of the models for 2 group, right? So, okay, it's a convenient model to construct 2 groups. So the cross module works like this. So it needs to have 2 groups and a morphism and the action of this one on that plus axioms. So the first group is just the group of all the invertible elements A. And the second group is a group of automorphisms and anti-automorphisms of A together. So it's automorphism plus anti-automorphism. And the map from here to here. So all of this, they act back on A. So they take invertible elements to invertible elements. That's the action of the second group on the first one. And the map from the first to the second is this. So because every element A gives me an automorphism. It doesn't give me an anti-automorphism, but it's not needed. It needs to be an automorphism. And the gradient comes from the gradient here, because obviously it has a subgroup. The even part is here. So this group and automorphisms is even part, and anti-automorphisms give an odd part. Questions? Cool. Now that's a visual picture of the same, of roughly this one categorical visual picture of this two group of automorphism of an algebra, right? So it has two objects, and you want to fill them up, algebra A and algebra with opposite multiplication. You have an automorphisms, they act here, and anti-automorphisms are isomorphisms between A and A opposite. They act like this. Right? And then somehow this is a two-group theoretic picture, because on every automorphisms, the maps between them are given by A, by invertible elements of A. So this is the picture I would have, right? And advance to the next animation. And here is our main theory, this message now. That for every C2 graded two representation row of G, and it's a two representation with the corresponding convolution I've written. Yeah, so it's one of the 8 possible convolutions. There exists a finite dimensional semi-simple algebra A and a homomorphism from G to this two group, inducing this two representation. So what is a homomorphism? Yes, so your G0, yes, acts on A by automorphisms, and G1 should act on this algebra by anti-automorphisms. And if it's a proper two group, if it's not just a group, but if it's two group, then there are this kind of, then it has two morphisms, and the two morphisms will act by multiplications of algebra. So, and what does it mean to induce this two representation? Let me explain. So in the model I wrote, I can explain it easily. Just take this algebra A, so it's finite dimensional semi-simple, just list all of its simple modules. This is a dimension of this two representation. And if I take an element, even element, right? If I take an even element, it acts on algebra A by automorphisms. So you can pull left modules to left modules under this map G. So there is a pullback under automorphism of a simple module. And then the matrix of vector spaces, which corresponds to an even element G, consists of all homomorphism from Si to pull back under Sj of phi j. That's the first formula. And then if you have an odd element, it acts on A by anti-automorphism. So if you pull a left module to, you're not going to get a left module, you're going to get a right module. But because it's all finite dimensional, you can take a dual, and that's what you're going to get. So the matrix will correspond to these homomorphisms from Si to, well, you take Sj, you take the dual. This was the left module, Sj. The dual is the right module, and the pullback of the Sj dual is the left module.
Can I ask you a question?
Sorry?
Can I ask you a question?
Yes.
G is necessarily a finite group, or we can develop this theory for compact or locally compact groups?
So for two representations, it's harder. I mean, for one representations, for usual representation theory, yes, compact group will work fine, and even locally compact group. Yes. With two representation theory, topological groups are not very friendly. So topological groups essentially do not act in an interesting way on Kapranov-Voevodsky two vector spaces. They may act on some other category of two vector spaces, but I don't know. So that's, and in general, the way we develop this theory, okay, we have a discrete group, but it works very well for two representations of C2 graded two groups with finite fundamental group. That's the finiteness condition we want. Somehow the two morphisms could be any, and with these representations, we could do induction, restriction. We've done lots of interesting stuff in that paper. And actually, this is the end of my talk. Sorry, I'm a bit too quick, but maybe there are more questions.
Well, I mean, thank you very much for your talk. My microphone was not working properly, but it seems that now it is kind of, it started working. So let's thank our speaker. So, any questions or comments? So, I mean, these two groups, are there, how shall I, for example, we have p-adic groups and so on in the classical group theory or in automorphic forms.
Right.
Are there two group counterparts of such objects, like two p-adic group kind of?
I don't know. Again, essentially, possibly yes. Somehow, the way to think, the kind of the best way to think about two group. Well, there are two kind of. Okay, there are. I never described two group. There are three ways to think about two group, similar to a group. One is that a group was a category where every object with one object and every morphism invertible. Similarly, a two group is a category, a two category with one zero object where every one and two morphisms are invertible. But that's very kind of, it's not very nice to work with. A better way is a topological way to think about two group. So a usual group is essentially one type of a topological space, because up to one type, a space is determined by its fundamental group. But a two group is a two type of a topological space, because somehow loops and homotopy between loops completely determine the topological space. And right next to it leads another interpretation. This is kind of strictification of a two group, because up to kind of lax automorphism, a two group is always given by a crossed module. And this is where possibly PID groups could come in, because a cross module is a pair of groups.
Right.
And then somehow they could have a topology. And I think, yes, in that sense, our additional structure would be kind of PID analytic or something else.
Thank you. That's a very illuminating, nice answer, actually. Yeah. So, any more questions or comments?
Excuse me, then could there be also a generalization, like instead of C2 graded, CK graded, or some other finite group graded?
Yes, absolutely. And again, it would be interesting to work out, right? So obviously, in terms of classical representation theory, what you'll need okay, so how should I say? The algebra of this is very interesting, because instead of C and R, instead of the two fields, you would need to consider Galois field extension. And then there are various interesting classifications of graded division algebras. And it's all kind of, the algebra of this is very, very rich. In terms of physics, it's probably not as interesting, because time has only two directions. Because the reason kind of physicists look at it, because there is the time can go back, right? You have symmetries which reverse time. And then in terms of topology, I'm kind of in two minds about that. So essentially, the way it comes to a topology is through kind of this KR theory, yes? So what happens is that you have a topological space on which your C2 graded group acts. And then you can see the complex vector bundles, which on which the group also acts. So it's equivariant vector bundles on your topological space, complex vector bundles, where your even elements kind of act normally, but odd elements walk antilinearly. Yes, like your usual, the standard KR theory, it's for group C2. Yes, so this is topological spaces with an involution, and the vector, the involution acts antilinearly on your vector bundles. So obviously, topologically, again, there are no kind of nice natural topological fields. Like C and R is the only kind of Galois extension interesting for classical topology. But there are all these beautiful unanalytic geometries now, and down prismatic spaces, and etc., where all sorts of other Galois extensions naturally appear. Fields with other Galois groups will appear. And then in all these environments, other K-series with kind of this nature would be interesting.
Well, instead of the time symmetries, aren't there space symmetries that are involved that might arise to some similar theory? Infinitesimal spatial variable symmetries of the space that leave some metric invariance.
Possibly. I'm not a physicist.
Okay.
I don't know. But possibly your space could be could have some other interest. Your space-time continuum may have some other discrete kind of interesting symmetries. Yes, I don't know. If you take, and then somehow other groups may be of interest. But these co-representations are of interest to crystallographers. So if you open books on crystallography, they have all this list of characters of co-representations. They call it something else. But for various crystallographic groups, for wallpaper and for dimension 3, for the important ones, they list all these co-representations and long tables.
Thank you.
Or comments? So then maybe we thank our speaker once more. Yeah. Thank you, Dimitri. It's a nice talk, actually. And I hope we can now stop the recording, maybe.